So when we look at Lewis structures, like I said, you're going to want to have something out that you're going to draw, and it's really important that you're able to erase easily. So this is where my iPad comes in handy because I can erase things on it pretty easily. But I used to do this with whiteboards. So if you have a whiteboard handy, um, these are kind of fun to write on whiteboards because you can erase really easily. The first thing I want to tell you about are the valence electrons. The valence electrons are the outermost S and P electrons. So like Nikhil was asking about that periodic table, grab that periodic table, whatever it may be, whatever it may look like. It doesn't matter which periodic table you have. And I want to make sure that we have all the same idea of what a valence electron is. So in this first column right here, these have one valence electron. Then we have two valence electrons, okay? That's two S valence electrons. Here, we don't talk about them very much. That's because they do have two valence electrons, but weird stuff happens. And then we go to 3, 4, 5, 6, 7 valence electrons. Now these guys have mostly 8, but again, they don't get involved in bonding, so we don't talk about them. These are metals, so they don't get involved in covalent bonding. So those are really the valence electrons that you need to know. And luckily for you, they match up with the group number. So group number 17 has 7 valence electrons. And that's to say that fluorine has 2 S electrons from over here plus 6 P electrons, which is, or plus 5 P electrons, which is what gives us 7 valence electrons. So that's what I'm talking about. They are, like I said, the outermost S and P electrons. They're the ones that get involved in bonding. Sure, there's a whole bunch of other electrons that are in atoms, but if they're not involved in bonding, who cares, right? So a Lewis dot diagram is a way of representing these outer electron arrangements. The first thing you do is write the chemical symbol, and then you give dots to indicate valence electrons. You put one on each side before you pair them. So let me give you an example here of, like, say, carbon. So carbon has 4 valence electrons. We say 1, 2, 3, 4 valence electrons. Oxygen has 6 valence electrons. We would draw its Lewis dot diagram like this: 1, 2, 3, 4, and now we can pair them: 5, 6. So you can see there that oxygen has 2 paired electrons, 2 unpaired electrons, which is going to make us start to see patterns. We know that electrons like to pair up, right? So carbon likes to pair 4 times, likes to bond 4 times because of those unpaired electrons. Oxygen likes to bond 2 times because it has 2 spots for unpaired electrons. We'll get into that later, but it's good if you start visualizing. Here are elements 1 through 20 on the periodic table. Let me even break this down even simpler, okay? First of all, when we're talking about covalent bonding, we are not talking about metals. So we can get rid of all the metals, all right? Their Lewis dot diagrams are there, they exist, but they don't really matter to us very much. The next thing I want to get rid of is the noble gases. All right, they don't get involved in bonding. They have 8 valence electrons. They have a full shell. They are happy. They are satisfied. So we don't really involve them very much. Now, helium is technically a noble gas, but helium only has 2 valence electrons. But helium is important because it shows us that hydrogen, with its 1 valence electron, is trying to be like helium. But since it's a noble gas and it doesn't get involved in bonding, we don't have to worry about it. The other one that we're not going to touch on too much this year is boron, because it's a little bit of an exception here, and you've got this big open space. So boron actually only bonds 3 times, and it becomes an exception. So take a look at that. We've really only got these Lewis dot diagrams that we even have to worry about, plus hydrogen over here. So it's really not that many when you start looking at your periodic table. It's not like you have 110 elements. I've got 9 of them here that you really need to think about. But you can see that carbon has 4 valence electrons, nitrogen has 5, oxygen has 6, and fluorine has 7. Everything below is going to follow the same pattern. So if you're below carbon, it's silicon. It also has 4 valence electrons. Like I was mentioning before, these are bonding sites. So carbon likes to bond 1, 2, 3, 4 times. Nitrogen likes to bond 1, 2, 3 times. Oxygen prefers, and you'll notice I keep saying likes to, prefers to, because this isn't always set in stone, but oxygen will often bond twice, and fluorine and all the rest of those guys, which we call the halogens, bond once. Okay, so this table right here, this picture really has more information on it than any of the rest of the pictures that I'm going to show you. Because of all the patterns that are followed on the periodic table. And then hydrogen over here is just trying to get one more electron to be like helium, so hydrogen only bonds once. Okay, hydrogen doesn't bond like 7 times or something like that. It doesn't work like that. You can't have that many bonds. So like I mentioned, atoms are most stable when they have 8 valence electrons in their valence shell. So when you're sitting there and you are neon, that's a noble gas, and you have 1, 2, 3, 4, 5, 6, 7, 8, everything is paired up. Boom, you are a stable atom, and you're most likely, as an atom, not going to be looking to bond up with anything. Let's take a look in disgusting detail here what a covalent bond actually is. A covalent bond occurs when 2 or more atoms pair up and they share their unpaired electrons. So whatever these are, okay, let's just, because we want to give them names, let's just pretend these are chlorine atoms, okay? And the chlorine on the left has 1, 2, 3, 4, 5, 6, 7 valence electrons. The chlorine on the right has 1, 2, 3, 4, 5, 6, 7 valence electrons. This area right here is the sharing. So you can see that they each have 8 valence electrons because they've each decided they're going to share that 1 valence electron. Now this is showing them in orbitals or like in perfect little lines, but we know that electrons are kind of buzzing around in orbitals. A single bond is when 1 pair of electrons is shared. A double bond is when 2 pairs of electrons are shared, and a triple bond is when 3 pairs of electrons are shared. So we've been seeing these as lines. Okay, that's what a triple bond has looked like to us. This is what a double bond has looked like to us. And here's what a single bond looks like. But if you start thinking about them as dots, as paired electrons, now they start looking like this. And sometimes the dots will run the other way. I haven't really found a person that tells me which way the dots have to run. So that's a triple bond, and you can see there that the nitrogen on the left has 8 valence electrons, and the nitrogen on the right has 8 valence electrons, and they're sharing those inside electrons. Oxygen is one that we talk about all the time that I keep showing you as an example. It's a great example of a nice, easy double bond. There's oxygen. Here's what we call those lone pairs that are hanging out there. The oxygen on the left has 8 valence electrons, and the oxygen on the right has 8 valence electrons. And that's where you get the double bond. This is my method. This is the way that I teach people how to do Lewis dot diagrams. I call it a bank method. Like I said, there's a lot of other ones out there, but I'm going to show you my method because I picked it because I think it's the simplest. So when I'm doing Lewis dot diagrams, I collect all available electrons in the Lewis dot diagram. I collect them all into a big bank. I imagine that when all of these atoms come together, they bring a certain amount of valence electrons, and then they divvy them up and they share them. That's not what everybody imagines, okay? If you watch that Professor Dave video that I showed you, he's showing you that one electron moves up, and that's fine. But my step number one is to add up all valence electrons, okay? That's from the group number. If you have a charge, so if you've got a polyatomic ion, you're going to add an extra electron. If you have a positive charge, which is just for ammonium, then you're going to take away an electron. But let's look at these examples down here. So you've got carbon, 3 hydrogens, a nitrogen, and then 2 more hydrogens. First of all, you might be asking yourself, why didn't she put all the hydrogens all together? Well, sometimes chemical formulas are telling you stories about the structures. So for whatever reason, they decided to put these hydrogens with the carbon. And that reason is because they're attached to the carbon and these hydrogens are attached to the nitrogen. So I just want to warn you, don't be thrown by it. But when we start adding, we have 4 valence electrons that come from the carbon. We have a total of 5 hydrogens, and the hydrogens each bring 1 valence electron. And then my nitrogen brings 5 valence electrons. I add that all together and I get a total of 14 possible electrons that can go into this. So when I start to draw this, and I'm getting a little bit ahead of myself, I can draw a C, an N. Like I said, it tells me a story. I know that the H's are all attached to the C, and I know that these 2 H's are attached to the N. Once I build this, then I can count in my electrons, okay? Now, without even noticing, I chose my central atoms. I chose carbon as a central atom, and I chose nitrogen as a central atom. Typically speaking, it's going to be the least electronegative. Let me give you a hint. Carbon always goes in the middle. Carbon likes to bond 4 times, so it'll go into the middle. Then things like nitrogen, then oxygen. You're never going to see hydrogen in the middle. Hydrogen only bonds once. So that's why I chose the central atoms that I chose there. Number 3 says arrange the other atoms around the central atoms. This is the rule that I was telling you about. Hydrogens and the halogens bond once. Oxygen family, everything below it, sulfur, bonds twice. Nitrogen, phosphorus bonds 3 times, and the carbon family bonds 4 times. So when I start looking at this, I can see here, I've got my carbon bonded 1, 2, 3, 4 times. My nitrogen is bonded 1, 2, 3 times. Then I start putting electrons from my bank. All right. I start filling all octets. So 1, 2, 3, 4, 5, 6, 7, 8 around the carbon. This 1, 2, 3, 4, 5, 6, 7, 8 is around the nitrogen, which is going to give us a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 total electrons, which is the number that I needed from my bank. All right, now you might be asking about the hydrogens. The hydrogens are happy only being bonded once or having 2 valence electrons. So if you just manage to follow that one, that's the hardest Lewis dot diagram that we're gonna do, all right? Hydrogen, like I said, is never the central atom. It forms only 1 bond. So it's going to be in the outer layer of atoms. Therefore, put them in last. Put your hydrogens in as an afterthought. And then this is what I just showed you. You put electron pairs around each atom so that there are 8 electrons. You follow this octet rule. Sometimes it's necessary to form double and triple bonds, which I will have to show you in a second. CNO O, P, and S will form multiple bonds. The rest of them typically are going to be single bonds. If you remember back to biology, these are the elements of life. All right, chomps or schnapps or whatever they call them in your biology classes. C, N, O, P, and S are the elements of life, plus everybody's little buddy, hydrogen. But hydrogen doesn't form double bonds. So let me show you the way that I would figure out a Lewis dot structure for CF4 or carbon tetrafluoride. The first thing I do is I'd make my bank. All right. So I find carbon on the periodic table. There's carbon. Carbon has 4 electrons. There's fluorine. Fluorine has 7 valence electrons. Then I would start my drawing. So I would say I've got 4 valence electrons from the carbon, and I have 7 valence electrons from the fluorine, and there are 4 of them, which gives me a total of 32 electrons in my bank. Choose the center atom. Well, I know that carbon's going to go in the center, and I know that carbon loves to bond 4 times, and I have fluorine, which likes to bond once. And then go ahead, start adding in electrons. Make sure you satisfy all octets. So there's my octet around that carbon. Here is my octet around the fluorine. And each one of these fluorines has to have an octet. Now, I don't necessarily recommend counting while you're drawing the dots, but you can if you want, because if you don't count while you put the dots down, then you have no idea how many you have. But after I go through and count these, I have 32 electrons. So I'm done. This is the Lewis dot diagram for CF4. Now you can see why I hate Lewis dot diagrams, because they're all like dotty and messy looking. I much prefer something that looks like this. This is how we turn a Lewis dot diagram into a structural formula. Each one of these pairs is represented by a line. And as far as lone pairs, you don't need to show them anywhere but the central atom. You can if you want, but you don't have to show them there. So you can see it's a lot less you have to draw. Now let's do a little bit more of a complicated one. Let's do CO, which is carbon monoxide. So the first thing I want to do is I want to get my bank. So I've got 4 electrons from the carbon plus 6 valence electrons from the oxygen, which is going to give me a total of 10 valence electrons. I don't have to pick a central atom because there are only 2 of them, C and O. All right, satisfy everybody's octet. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, I've exceeded my bank. I have too many dots from my bank. So what I need to do is you need to lose an electron pair, you need to lose an electron pair, and you're going to share an electron pair. Okay? When you remove an electron pair from each of them, then they share an electron pair. I can go back and count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've decreased it, but not enough. So again, you're going to lose an electron pair. Now, you might think like, oh, take this electron pair away. It doesn't matter. You can take this electron pair away. It's the same thing. All right? It really is, because they're not like, it's nothing that we have to do. They have to share another pair of electrons. Now, that looks really ugly, so I'm going to rewrite it, and I'm going to say that they're sharing this 3 pairs of electrons, and then they each have a lone pair there. In other words, it's a C triple bonded to an O. That's the Lewis dot structure for carbon monoxide.
Miss Robles,
Yeah.
After you draw those three lines, won't you put like the two dots on each side of the carbon and oxygen?
Optional. You
Oh, okay.
can if you want. You can if you want. The general rule is you only have to have it on the central atom for me, and eventually even that rule goes away. All right, now I showed you carbon monoxide. It's worth showing you carbon dioxide, right? CO2, because that's the one we talk about more often. So again, I get my bank. I have 4 from the carbon, plus I have 2 oxygens, which each have 6 apiece. So I have a total of 12 electrons from oxygens and 4 from carbons. So I'm bad at math, but I believe I have 16 electrons in my bank. All right. Now this time I've got 2 oxygens, so I'm going to go ahead and draw the C in the middle. It's the least electronegative. And I'm going to draw an oxygen and an oxygen around the outside. My next step is to satisfy the octets. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I have too many. I don't have that many electrons in my bank. So this is where the eraser comes in. You got to share. If you've got too many
Miss
electrons,
Robles,
you've got to share. Yep.
I just wanted to make sure like the element which has the subscript, generally you should put the valence electrons in for that, right?
So right here, this 2 means
Yeah.
that there are 2 twice as many oxygen atoms. So you need 2 times as many electrons.
Also, six is like the valence electrons, right?
Yes. 6
Okay.
is the valence electrons.
Miss
All right.
Robles,
Yep.
how come when you like do it, you just put dots around all of them?
Well,
Like,
because again, this is kind of my method. There's other ways to do this,
oh,
but I want to make sure at the end of the day, all electrons are satisfied. All atoms have 8. So if I don't do it ahead of time, I may forget someone. Just kind of the way I do it. And like I said, this way you'll never have like extra floating electrons that you don't know what to do with. So if I have too many, I erase. If you don't have enough bicycles for everybody in the family, you got to share a bicycle. So you lose a pair, and now you're going to share a pair of valence electrons. I chose to erase those ones. It really doesn't matter which ones you choose to erase, as long as one comes from one of the atoms and one comes from another one. Now, if I were to go back and count again, I would get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So I still have too many. So again, I have to take a pair from the oxygen. I'm just going to take this pair. And I got to take another pair from the carbon. Luckily, they have another pair that isn't shared. Go ahead and make them share another pair. And lo and behold, now I have 16, which is the perfect number from the bank. I can go back and double check. And I can see here that my carbon has 8 valence electrons. And each one of my oxygens has 8 valence electrons. And if I want to redraw that in, lines, then it looks like this. It's a C double bonded to an O, double bonded to an O. And you don't need to put these valence electrons unless you really want to put those valence electrons. They don't really tell a story about the shape because the shape of that is going to be linear. So that is how we start showing Lewis structures. All right.
Miss Robles,
Mhm.
so to like check yourself, each one has to have 8.
Yep. And that's why at first, when I very first start doing it, I do the circles. I draw those circles around them because I check to make sure it has 8. And then like the way I did the overlapping circle, I make sure that one here has 8, one here has 8.
Wait, so when we're doing like the Lewis dot things, are we supposed to have the lines or just only keep the dots?
It'll be, first of all, you're never going to draw anything for me on a test, but what I'm going to say to you is what I would say to anybody. You should be able to recognize anything. You should be able to be bilingual in that. That's a good question. All right. So there's exceptions to the octet rule. For example, boron is a pesky exception. Boron, look at right here, is satisfied with just 6 valence electrons. And then there's ones that actually get more than 8 valence electrons. We're not going to visit these this year. We'll save those for another time. I just want you to know that they exist. All right, so the next step is to then start giving shapes, right? Start doing Lewis dot diagrams and giving shapes. So this says, give the shape of the following. Now you might look at that and know right away what the shape is, but it is important to realize it's not always as obvious as you think. So the shape of HCN, I like this board better because I can erase on it, is we're going to take a look at it. So here's HCN. I get 1 valence from the H plus 4 from the C plus 5 from the N, which gives me a total of 10 valence electrons. I go through. I like to satisfy the octet. N goes on the right and C goes in the middle because it's less electronegative. Hydrogen never has 8. Hydrogen only ever has 2. So its octet is satisfied. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can see I'm already out of stuff on the bank there, but keep drawing. 11, 12, 13, 14. Okay. So we only have 10 in the bank. They've got to share. You lose a pair, you lose a pair, you share a pair. Okay, count them again. 2, 4, 6, 8, 10, 12. Still too many. You lose a pair, you lose a pair, you share a pair. Now, if you looked at that and you were like, hey, I think I knew that without drawing it out, because I remember you told me things like hydrogen bonds once, carbon bonds 4 times, and nitrogen bonds 3 times. Cool. Good for you. You're awesome. You're already starting to see kind of the next level of chemistry here. And that's okay if you're seeing it or not seeing it. That's why sometimes people tend to even skip over the Lewis dot diagrams, because at the end of the day, right here, what I drew this red box around is what matters, because the shape of that is linear. All right. The next one is CH2F2. So this is a little bit of a bigger one, okay? CH2F2. Again, some of you might be looking at that right away and you might be like, boom, I already know how this entire thing is put together. If not, let's add them up. 4 from the carbon, plus we have 2 from those hydrogens, plus we have 2 from the fluorines, or I'm sorry, 2 times 7 from the fluorines. So we have 14 from the fluorines, which equals 20 electrons, right? We put the carbon in the middle. We put fluorines around the outside. If you don't like the fluorine there and you'd rather draw the fluorine there, that's fine. This is a 3-dimensional object. Nothing is set in stone. It can spin in space, so don't even worry about that. And then we satisfy all octets. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And look at that. It came out perfect. It's 20. There's 20 electrons in the bank, so we're all set. So we end up with a C, single bonded to an F, single bonded to another F, single bonded to H, and single bonded to H. So the name of this is a tetrahedral shape. All right. Notice the hydrogens, please, please, please don't ever put 8 electrons around a hydrogen. That's a really big mistake I see people make a lot. And then they'll be like, whoa, I got so many over my bank. Your hydrogen is only bringing 1 electron. It can't end up with 8. This is a fun one. NO2 with a -1 charge. So that is a polyatomic ion. NO2 with a -1 charge, right? We get 5 electrons from the nitrogen, plus we get 2 times 6 from the oxygen, which is going to give us 12, plus we've got this. That -1 tells me that I have an extra electron in my bank. Don't forget it. The -1 is really important. So I get 12 plus 6 is 18 electrons. I can go ahead and draw them out here. I've got an N and an O and an O. Satisfy the octets. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Oh
Can you
no.
explain once again why there is +1?
Yes, you take it away if there's +1. Yep, it means it lost an electron.
Ms.
But
Robles,
yep,
does every atom have 8 except for hydrogen?
yes, or every atom wants to have 8 except for
Okay.
hydrogen.
So
And then
like when you're sketching it, you draw
Yep.
8 for all of them except when it's hydrogen?
Yep. And then there are some other exceptions, but we don't talk about them, like boron. So I've got too many here. I've got 20. So in order to decrease, I take this away. I take this away. That has decreased a pair here. And now I end up with that. Now the original question was the shape. So let's redraw this and think about Vesper. I've got a nitrogen here with this lone pair. The lone pair matters on the central atom. So a nitrogen single bonded to an oxygen, double bonded to another oxygen. And the shape of this is bent. And more specifically, it's bent at 120, right? So even though you finish up your drawing and it looks like this, and a lot of people look at that drawing and they say, hey, that's linear. That's not what you're going to end up with. You've got to remember Vesper, and you've got to remember how those lone pairs are going to push things down in the other direction. Don't forget everything that we've talked about. Okay. C2H4. Carbons love to bond to each other. So C2H4. I get 2 carbons. They each bring 4 each. That's 8 electrons plus 4 from those hydrogens is going to equal 12 electrons. All right. Carbon bonds to itself, and then you can put the hydrogens around it. Now, you might want to put a hydrogen here and a hydrogen here, but I think that looks pretty uneven. So instead, I'm going to put 2 hydrogens on one and 2 on the other. I'll tell you that if you had done that, you would have ended up okay. So let me pretend that you did that, and I'll show you what it means to end up okay. Satisfy everybody's octet. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right. So again, I have too many. I have to make this carbon lose electrons. This carbon has to lose electrons. And it's bonded to all these hydrogens. So I'm just going to pick up that hydrogen and I'm going to move it over to here. All right. So it's actually, it turns out okay. And then they share their electrons, which makes me end up with this beautiful shape here. A C double bonded to a C, single bonded to these H's. You'll notice I'm spreading them out. I'm trying to think about Vesper when I redraw them, because at the end of the day, it was asking me what the shape was. Here's that shape around that carbon. It's a trigonal planar, right? And it turns out that it's a trigonal planar around both carbons. All right, a little bit tricky, a little bit advanced, I think there. SCl2, a couple more examples and then I'll stop the torture on you. So there's SCl2. S is just like oxygen. S has 6 valence electrons, plus we have 2 from those chlorines. So it's 2 times 7 or 14 equals 20 electrons. So I can put the S in the middle because it's the furthest to the left. Another way I think about it is it has the least amount of electrons or the most bonding sites, with the exception of hydrogens. So again, satisfy the octets. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Boom. Now the question was about the shape. You may look at that shape and you may be like, linear, but that's just because I tend to always draw things in lines. I encourage you to pay attention to lone pairs and redraw, right? We've got a lone pair here on the central atom and a lone pair there on the central atom. And when we have lone pairs on the central atom, all right, they're important to us. Here's that lone pair, here's that lone pair. And then I'm going to take the Cl and I'm going to put it in this direction and the Cl and put it in this direction. So this actually turns out to be a bent shape. And it's actually bent, if you care, at 109. So again, I really, really encourage you to make sure you don't look at that and you don't see a linear thing there.
Mr. Robles?
Yep.
How'd you know that was 109 and not 120?
Because at the end of the day, I have 1, 2, 3, 4 things attached to it. And if I have 4 electron domains, I have 109. If I have 3 electron domains, then I have 120. So it was because there was 2 lone pairs instead of just 1 lone pair. Okay, so examples, I think that's the last official example. I've got a bunch of other examples that I have for you to go through. I think, one says the shape and one says the polarity, and you could watch me do these all day, but I have the answers that I'm going to send out to you I'll send it out in a Schoology post. But basically there's practice the shape, practice the polarity, practice the intermolecular forces. It's kind of up to you at this point how much you'd like to practice of these, okay? And how many of these you want to do. I actually gave the polarity, the shape, the Lewis dot diagrams. I gave everything for all of them so you could have all of the practice for these that you need as far as the last little part of the notes there. You also can work on the worksheet. There's another worksheet that I have. It's called Practicing Lewis dot diagrams. I've put the answers up. So at this point, it's kind of whatever you want to do to practice.
As a